Ancient civilizations once powered their world without burning a single fossil fuel. This video uncovers 20 lost energy systems from the pre-industrial era, revealing how our ancestors achieved incredible feats by working in harmony with nature. You will learn how to apply these forgotten principles for a more sustainable future. We will explore how the Romans built gravity-fed factories and why medieval engineers constructed machines powered solely by the tides. What do you believe is our greatest lesson from the past? Rome's aqueducts were far more than just channels for water. They were the arteries of a hidden power grid. These graceful stone structures did not simply quench the thirst of a million citizens. They harnessed the relentless pull of gravity to drive industry. At the end of their long journey, water did not just spill out, it was put to work. It was channeled into mills where the descending torrent slammed into paddles, spinning great wooden wheels. These wheels turned gears that ground grain into flour, sawed wood, and even operated simple machinery. This was not a small-scale operation. The Roman engineer Vitruvius left us detailed plans describing how the force of falling water from an elevated channel was precisely calculated to maximize its work. The proof lies in places like the Barbegal Mill complex in southern France. Here, an entire hillside was transformed into a factory powered solely by water. A single aqueduct fed a cascading series of at least 16 separate water wheels, each one driving a millstone to produce flour on a scale that would not be seen again for over 1,000 years. This was the pre-industrial equivalent of a massive power plant, all running on the simple, clean energy of moving water. It makes you wonder, with our modern materials and knowledge, how many of our own energy needs could be met by revisiting such elegant, gravity-fed designs. This mastery of water was just the beginning, as medieval engineers looked to an even more powerful and predictable force, the ocean itself. While the Romans mastered the power of falling water, another civilization was perfecting the art of harnessing the wind itself, not to turn mills but to defy the desert heat. In the heart of ancient Persia, a skyline was not defined by smokestacks but by elegant, towering structures called bagirs or windcatchers. These were not decorative elements, they were sophisticated natural cooling systems built entirely from mud brick and intelligent design. A bagir worked by capturing the slightest breeze high above the ground and funneling it down a vertical shaft directly into the heart of a building. But the true genius lay in what happened next. That captured wind was often directed over an underground pool of water or through a network of underground canals known as kanats. As the dry, hot air passed over this cool moisture, it triggered a powerful cooling effect through evaporation, transforming the air into a refreshing, cool draft that would circulate through living spaces. The entire process required zero electricity, only an intimate understanding of airflow and water. The city of Yazd in Iran stands as a living museum of this technology, where these silent, graceful towers have provided comfort for centuries. It is a powerful reminder that comfort does not always require complex machinery. Sometimes it just demands that we listen to the natural rhythms of the earth. If ancient architects could create air conditioning from wind and water, what other natural forces did they turn into tools for living? This line of questioning leads us underground to a source of power as constant as the planet itself. Beneath the marble floors of a Roman bathhouse, an entirely different kind of energy system was quietly at work. While windcatchers cooled desert homes, ancient engineers in Greece and Rome perfected a method to generate warmth from the ground up, a system known as the Hypocaust. Imagine stepping into the vast baths of Caracalla on a cold day, your bare feet meeting not a chill, but a soothing, even warmth radiating from the floor itself. This luxury was not magic, it was a masterpiece of thermal engineering. A wood-burning furnace, the prefernium, was kept blazing constantly in a service room. The hot gases and smoke from this fire did not simply vanish up a chimney. Instead, they were carefully channeled through a hidden network. The floors were raised on countless short pillars of brick, creating a hollow space, while rectangular tubes were embedded inside the walls. The hot air would flow through this entire labyrinth, slowly releasing its heat into the stone and marble above before finally escaping through flues in the roof. This was a central heating system on a grand scale, warming every room in the complex without a single radiator or electric coil. The design required a profound understanding of thermodynamics, ensuring a steady draft to keep the air moving and to prevent deadly smoke from filling the rooms. The ruins of Pompeii offer a frozen snapshot of this technology, revealing the intricate brick pillars and flues that once made villas and public baths havens of comfort. This sophisticated use of heat raises a compelling question. If Mediterranean cultures could heat entire buildings so effectively, how did people in even colder regions manage to survive the harsh winters? Their solution was surprisingly organic, turning not to fire, but to the natural warmth generated by life itself. While Romans warmed their marble floors, families in ancient China found warmth in the very structure of their homes. In rural villages facing brutal winters, the Kang was not just a piece of furniture, it was the heart of the household. This was a raised platform built from brick or hardened earth, but it was hollow inside, functioning as both a bed and a stove. The process was simple yet brilliant. A small fire would be lit in a stove attached to the side of the platform, often used for cooking the family meal. Instead of letting the precious heat and smoke from that fire vanish up a chimney, it was ingeniously channeled through a network of flues that snaked through the hollow interior of the Kang. As the hot gases traveled this twisting path, their thermal energy was slowly absorbed by the thick, earthen mass of the bed. The smoke, now cooled, would finally exit through a chimney on the far side of the house. The result was a sleeping platform that stayed warm throughout the entire night, radiating a gentle, comforting heat long after the fire had died down. This was not merely about comfort, it was a masterclass in energy efficiency. By capturing waste heat from cooking and using it to heat the sleeping area, the Kang conserved precious fuel, making a limited supply of wood or coal last much longer. Historical records from the Ming Dynasty praise the Kang for its role in daily life, a cozy gathering spot where families would eat, talk, and sleep, all warmed by the same frugal fire. Its design was refined over centuries, with variations in size and flue patterns to suit the specific cold of different regions. Even today, in parts of northern China, you can find modern versions of the Kang still in use, a testament to a design so effective it has endured for over 2,000 years. It transforms our understanding of an energy source, turning the simple, everyday act of cooking into a system for home heating. But what if human effort itself could be captured and stored? This idea leads us to one of the most universal and ancient power sources, the energy of our own bodies. High above the cobblestone streets, a different kind of engine drove the skyward reach of Gothic cathedrals. It was not the rush of water or the push of wind, but the steady, rhythmic pace of human feet inside a massive wooden wheel. The treadwheel crane transformed the simple act of walking into a formidable source of lifting power. Picture a giant hamster wheel, but built for a person, often 2 stories tall and constructed from heavy timber. A worker would step inside this great wheel and begin to walk, his body weight and momentum causing the entire structure to rotate. This rotation turned a central axle, which was connected through a series of wooden gears and pulleys to a long wooden boom and a heavy rope. The genius of the gearing system meant that the slow, powerful rotation of the wheel was translated into a controlled, steady pull, allowing a single man to hoist stones weighing over a ton to incredible heights with remarkable precision. Chronicles from the construction of Notre Dame de Paris describe how these cranes perched on the rising walls, their human engines enabling masons to place massive blocks of limestone with an accuracy that animal power could never match. What made this system so brilliant was its on-demand nature. Unlike a watermill that needed a flowing stream or a windmill that required a steady breeze, the treadwheel crane provided power exactly when and where it was needed, directed by human intelligence. A surviving example, carefully restored at Canterbury Cathedral, stands as a silent testament to this human-powered marvel. It forces us to reconsider the very definition of strength, reminding us that coordinated human effort, amplified by simple machinery, could achieve what seems, even to our modern eyes, nearly impossible. If a person walking in a circle could lift the stones of a cathedral, what immense force could be unlocked by harnessing the patient, relentless power of the animal world? The patient strength of a horse became the engine of entire communities across the Viking world. In settlements far from fast-flowing rivers, the rhythmic clopping of hooves on packed earth signaled a different kind of mill at work. A single horse harnessed to a long, sweeping beam would walk an endless, patient circle. This was the horse mill, a simple yet brilliantly effective system that translated animal muscle into rotational power. The beam was connected to a central vertical shaft, and through a set of sturdy wooden gears, the slow, horizontal circling of the horse was transformed into the rapid, vertical spin of a millstone. This grinding stone, turning against a stationary base below, could crush grain into flour with a consistency and speed that human hands could never match. Norse sagas and archaeological finds of stone foundation rings confirm these horse engines were a cornerstone of daily life, providing a reliable power source that freed communities from total dependence on the whims of weather or geography. At the Folkviken Museum in Sweden, a carefully reconstructed horse mill demonstrates the elegant practicality of the design. A central pivot kept the animal on its circular path, while a simple harness allowed the horse to work for hours with minimal guidance. This was not a technology of conquest, but one of sustenance, enabling farming settlements to thrive in landscapes where other power sources were scarce. It represents a profound partnership between human ingenuity and animal strength. Yet, for all its reliability, this system still depended on the care and feeding of a living creature. What if you could build an engine that never grew tired, never needed food, and drew its power directly from the sky? This question would find its answer in the sweeping sails of a different machine altogether. Across the arid plains of Afghanistan, a unique silhouette pierces the sky, not a towering windmill with spinning arms, but a sturdy, cylindrical structure topped with whirling cloth sails. These are the vertical axis windmills of Nashtafan, and for over 1,000 years they have been harnessing the desert winds to grind grain with a quiet, relentless efficiency. Their design is a masterpiece of adaptation. Unlike the familiar horizontal windmills that must constantly turn to face the wind, these Afghan mills operate on a vertical central shaft. Their sails, made of cloth or reed mats, catch the wind from any direction, spinning the entire assembly around its central core. This brilliant simplicity made them perfectly suited for the unpredictable, gusty winds of the high desert, requiring no complex mechanisms to reorient themselves. Local communities built and maintained these mills using locally sourced materials like wood, clay, and cloth. The mechanics were beautifully minimal with very few moving parts. This not only made them easy to repair, but also ensured they could withstand the harsh, sandy environment for generations with minimal wear. The name Nashtafan itself translates to storm's sting, a testament to the powerful winds these structures were built to tame. Even today, a row of these ancient windmills continues to operate, their wooden gears groaning and cloth sails flapping as they have for centuries, a living museum of sustainable technology. It is a humbling sight that makes you wonder if such a simple, durable design could serve a community for a millennium. What lessons are we overlooking in our pursuit of complexity? This exploration of wind's versatility naturally leads us to a place where two powerful elements were combined, where the constant ocean winds met the endless pulse of the sea. The wind that swept across the Netherlands did more than just push water. It drove the very saws that built a global empire. Dutch engineers transformed the classic windmill into a powerful industrial tool, the wind-powered sawmill. This was not about grinding grain, but about mechanizing one of the most labor-intensive tasks of the age, cutting timber. Inside these mills, the relentless rotation of the wind-driven sails was ingeniously converted into a precise back and forth motion. A system of cranks and gears, often made of heavy wood and iron, transformed the circular power into the rhythmic stroke of a saw blade. This mechanical marvel could slice through massive logs with a speed and consistency that human hands wielding pit saws could never hope to match. The entire process was optimized for efficiency, with adjustable sails that could be fine-tuned to capture every bit of available wind, and a clever mechanism that automatically fed the next log into position for cutting. It was a production line powered by the sky. The famous De Rat windmill in IJLST stands as a restored monument to this innovation, its internal gears still poised to turn, a testament to the engineering that fueled the Dutch Golden Age. By enabling the rapid production of standardized planks and beams, these sawmills allowed for the swift construction of the merchant fleets and warships that made the Netherlands a maritime superpower, while also supplying the wood for its iconic canal houses. This system represents a pivotal moment where renewable energy was no longer just for food or water, but for full-scale industry. It makes you wonder, if wind could power entire factories, what other elemental combinations did pre-industrial engineers devise? Their next great leap was to forge a tool that blended the primal force of fire with the invisible power of air. Deep in the mountain forests of feudal Japan, fire and air were forged into legendary steel. The Tatara furnace was more than a simple kiln. It was a living, breathing entity, a clay box where masters orchestrated the transformation of iron sand into the revered Tamahagane steel. This was not a process of brute force, but of exquisite control. Teams of workers, often entire village communities, would labor for days, feeding the furnace with vast quantities of charcoal and the region's unique black iron sand. The heart of the entire operation was a massive set of manually operated bellows. Workers, moving in a tireless, synchronized rhythm, would pump these giant leather bellows, forcing a continuous stream of air into the base of the furnace. This was the system's lifeblood, raising the internal temperature to a point where impurities were burned away and the iron carbonized into high-quality steel. The master smith was like a conductor, reading the color of the flames and the sound of the fire to know precisely when to add more fuel or adjust the airflow. A miscalculation could ruin the entire batch, a multi-day effort lost in an instant. The prized result was a lump of Tamahagane steel, a heterogeneous material with varying carbon content that master swordsmiths would later fold and hammer countless times to create the legendary katanas, blades known for their unparalleled sharpness and resilience. The fact that this method is still practiced today in preservation societies is a testament to its profound cultural and technical significance. It represents a peak of human-scaled metallurgy, where skill and natural force were perfectly balanced. Yet, the sheer physical effort required by the bellows operators makes you wonder, how did other cultures manage to achieve the blistering heats needed for metalwork on a larger scale? Their solution was to replace human lungs with the relentless power of flowing water. The rhythmic thunder of a heavy hammer, powered not by muscle but by a flowing river, echoed through medieval European valleys. This was the heart of the water-powered hammer mill, a revolutionary system that turned the blacksmith's forge into a proto-factory. A large water wheel turned by a diverted stream spun a horizontal shaft. Along this shaft, strategically placed wooden cams, essentially protruding bumps, would catch against the end of a long, pivoting hammer arm. As the shaft turned, the cam would lift the heavy hammerhead high into the air. At the peak of the lift, the cam would release, and gravity would send the hammer crashing down onto a piece of red-hot iron placed on an anvil below. This trip hammer mechanism delivered a blow of immense, consistent force over and over again without the smith ever raising a sweat. The system's brilliance was its adaptability. By controlling the flow of water to the wheel, operators could regulate the speed of the shaft and thus the frequency of the strikes. A faster flow meant a rapid, pounding beat suitable for drawing out long bars of iron, while a slower, more deliberate rhythm was perfect for the final shaping of a tool. Historical records from the early Industrial Revolution highlight how these mills dramatically increased output in ironworks, producing everything from nails and scythes to the anchors for sailing ships. At places like the preserved Aberdale industrial hamlet in England, you can still see the entire integrated process, where a single mill pond powered not only the forge hammers but also the bellows that kept the furnace fires blazing. It was a fully water-powered production line centuries before the age of steam. This mastery over water's brute force to shape metal leads to an equally important question. If water could be used to pound solid iron, how could it be employed for the more delicate task of raising water itself to nourish crops? The relentless pounding of the water hammer gave way to a quieter, more persistent rhythm in the farmlands of the ancient world. Here, the challenge was not to shape metal, but to defy gravity itself, to lift life-giving water from a low river up to the thirsty fields on its banks. The solution was a masterpiece of elegant geometry, the Archimedes screw. Picture a long wooden tube wrapped around a central core, like a gigantic, open-threaded screw enclosed in a cylinder. One end of this device was lowered into a river or canal, while the other was angled up toward the irrigation ditch. A worker, or sometimes an ox, would turn a crank, rotating the entire screw within its casing. As it turned, the spiral chambers trapped pockets of water at the bottom, carrying them steadily upward along the threads until they spilled out at the top. The system was brilliantly simple, using the principle of an inclined plane to achieve what direct lifting could not. Its design, attributed to the brilliant Greek mind of Archimedes, created a continuous, gentle flow with remarkably little friction. This made it incredibly durable and able to handle silty, muddy water that would clog more complex pumps. Historical records from ancient Egypt and Mesopotamia show how these screws transformed agriculture in flat, arid regions, allowing farmers to cultivate land that would otherwise lie barren. The water lifted by this simple rotation nourished the crops that fed empires. Its legacy is a testament to functional design, so effective that modern engineering has not retired it. You can still see Archimedes screws in use today, not for irrigation but in wastewater treatment plants, where their robust, non-clogging action is perfect for moving thick, sludge-laden water. It makes you appreciate a design so perfect it has remained virtually unchanged for over 2,000 years. This simple machine solved the immediate problem of moving water, but it sparks a deeper question. How did societies capture energy not for immediate use, but for a time when it was needed most? Their answer was to build a battery not of chemicals but of pure, stored height. The sheer force of a falling weight could shatter castle walls. In the era of the trebuchet, gravity itself became a weapon of war. These colossal machines were not powered by tension like a catapult, but by the simple, devastating act of a massive counterweight plummeting earthward. Picture a long pivoting arm with a heavy wooden box filled with tons of stone or sand on the short end, and a sling cradling a large stone on the long end. To fire it, crews would use a winch to painstakingly raise the counterweight high into the air, locking it into place. This act stored immense potential energy in that elevated mass. When the trigger was released, the counterweight fell, whipping the long arm upward in a violent arc. The sling would unfurl at the perfect moment, leveraging the arm's motion to launch its projectile in a high, arcing trajectory. This was gravity converted directly into kinetic force. The engineering was remarkably sophisticated. By adjusting the weight in the counterweight box or altering the length of the sling, operators could fine-tune the range and impact point with surprising precision. Historical accounts describe some of the largest trebuchets, like the Warwolf used against Stirling Castle, being capable of hurling stones weighing over 300 pounds across distances of several hundred yards. Modern reconstructions, such as the working machine at Warwick Castle, bring this terrifying power to life, the deep thud of the falling weight and the swoosh of the projectile making the physics feel visceral. Yet this mastery of balanced forces and falling weights was not confined to warfare. The same principles that could launch a boulder were soon harnessed for a far more peaceful and profound purpose, the steady, silent measurement of time itself. The same principles of controlled, falling energy that powered the trebuchet found a far more delicate application within the silent walls of a medieval monastery. Here, the steady drip of water replaced the crash of a counterweight, marking the passage of hours with divine precision. Monastic life revolved around the canonical hours, the set times for prayer that structured the entire day and night. To maintain this sacred schedule, monks turned to an ingenious machine, the water-powered escapement clock. At its heart was a constant flow of water, often from a small, elevated reservoir that fed a stream into a receiving vessel. But this was no simple water clock that just filled up. The true breakthrough was the escapement mechanism. Imagine a water wheel, but one designed to turn in tiny, precise increments. As water filled a series of small cups on the wheel, the weight of the water would eventually tip a balanced lever, releasing a pallet that allowed the wheel to advance just one notch. This action would simultaneously block the next cup and open a drain, emptying the one that had just tipped. This cycle of catch and release, repeated endlessly, created a regulated, oscillating motion that could be translated through a gear train to move a single hand across a dial. It was a heartbeat for the machine, a way to break the continuous flow of water into discrete, measurable units of time. The entire system, with its carefully maintained reservoirs and floats, was a masterpiece of hydro-mechanical engineering, ensuring water pressure remained consistent so the tempo of the ticks never wavered. This was not merely about telling time, it was about synchronizing human activity with the cosmos itself. Far beyond Europe, in 11th century China, the brilliant engineer Su Song constructed a colossal water-driven astronomical clock tower over 30 feet tall. His device used a massive water wheel with a sophisticated escapement to not only tell the time, but also to rotate an armillary sphere for observing stars and a celestial globe that mapped the heavens automatically. These early energy systems transformed the invisible force of gravity acting on water into the very framework of ordered life. but a clock tethered to an aqueduct or a massive tower could not be moved. This limitation sparked a new quest, one that would lead to a source of power you could hold in your hand. A trigger pull could unleash a force stored for hours, even days, within a carefully crafted piece of wood and bronze. This was the genius of the spring-powered crossbow, a weapon that transformed ancient battlefields by turning stored mechanical energy into a soldier's greatest advantage. Unlike a standard bow that required the archer to hold the draw with their own muscle power, the crossbow used its own rigid frame. A soldier would place his foot in a stirrup, lean over, and use the full strength of his back and arms to draw the heavy bowstring back, bending the powerful laminated arms of the bow, often made from wood, sinew, and horn. This action loaded the weapon with potential energy, locking it in place with a precision bronze trigger mechanism. That energy remained trapped, ready and waiting, until the moment a release was needed. Historical texts from China's Warring States period describe how massed units of crossbowmen could unleash volleys of bolts with devastating range and penetrating power, striking down armored opponents before they could even get close. The true marvel was the trigger assembly itself, an intricate bronze box found in the pits of the terracotta army. Inside, a series of 3 precisely fitted levers and a rotating lock, known as the Chinese trigger, held the immense tension safely. Pulling the trigger lever initiated a cascade of movements, dropping the lock and releasing the string with a sharp, violent snap. This system allowed a single soldier to aim and fire a weapon that possessed the power of a much larger bow, all because the energy had been loaded and stored in advance. It was a handheld battery of kinetic force. This mastery of storing energy in a spring-like arm makes you wonder, how did engineers begin to manage the opposite process, the continuous conversion of human motion into smooth, rotational energy? The answer lies in a simple device that put a new kind of spin on manual labor. The simple rotation of a hand crank could transform a handful of grain into the flour for a family's daily bread. Before the rise of centralized mills, the rhythm of the hand-cranked grinder was the heartbeat of countless households. This was energy production at its most personal and direct, where human effort was immediately converted into the mechanical work of survival. The most basic form was the saddle quern, a simple stone base with a smaller, hand-held stone that was rubbed back and forth to crush the grain. But the true innovation came with the rotary quern, a device that used a rotating handle to turn an upper millstone against a stationary lower stone. This circular motion was far more efficient than the back and forth grinding, allowing for a continuous, smooth action that produced a finer flour. The design was brilliantly adaptable, crafted from whatever materials were at hand, from local granite in Roman Britain to volcanic rock in the Americas. The Mexican metatare, a flat, slightly curved stone used with a cylindrical mono, is a perfect example of this enduring technology. For thousands of years, this simple tool was central to life, used to grind not just corn for tortillas, but also spices and medicines, its surface worn smooth by generations of use. This daily act of grinding was a profound partnership between person and tool, a direct application of energy that sustained communities, but it also required an enclosed, often smoky, indoor environment. This constant need for fresh air in tight spaces led to another brilliant innovation, one that harnessed the flow of air itself to make homes livable. A gentle desert breeze did not just whisper past an Egyptian home, it was actively captured and channeled inside. High on the rooftops of ancient dwellings, a distinctive tower called a malkaf, or wind scoop, reached up to harness the prevailing northerly winds. This was not a complex machine, but a brilliant architectural feat. The malkaf was an open, V-shaped structure perfectly angled to face the dominant wind direction. As air rushed into this wide opening, it was funneled down a narrowing shaft, its speed increasing due to a principle we now call Bernoulli's effect, the same force that lifts an airplane wing. This accelerated stream of air was then directed down into the main living quarters, creating a constant, refreshing cross breeze that flushed out hot, stagnant air and replaced it with cooler drafts from outside. The ruins of the city of Tel El Amarna provide clear archaeological evidence, showing how these wind scoops were a fundamental element of domestic architecture, carefully integrated into the layout of elite residences for maximum comfort. But the system did not work in isolation. The captured wind was often guided over a central courtyard, where a shallow pool of water or even just moistened charcoal mats awaited. As the dry air passed over this water, it would pick up moisture and cool down significantly through evaporation, transforming a simple breeze into a form of natural air conditioning. The entire home became a passively cooled sanctuary, a refuge from the blistering heat outside that required no energy input beyond its initial, intelligent construction. It is a level of sustainable design that modern architects are only now rediscovering, with contemporary passive cooling studies frequently citing the Malkaf as a model of efficiency. This mastery of airflow makes you wonder, if ancient builders could so effectively harness the invisible power of the wind, what could they achieve with the most abundant and visible energy source of all, the sun itself? The sun itself was an architect in ancient Rome and Greece. Entire villas were carefully oriented to capture the low winter sun, transforming their very walls into a free and silent heating system. This was passive solar design, a sophisticated understanding of solar gain that required no moving parts, only brilliant planning. Architects like Vitruvius wrote extensively on the importance of siting a building, instructing that living quarters and baths should face the winter sunset to soak up every possible ray of warmth. The key to this system was thermal mass. Floors and walls were built from thick stone, tile, or even earthen materials that possessed a remarkable property. They absorbed heat slowly throughout the day. Then, as the temperature dropped after sunset, these materials would gradually release their stored warmth, radiating it back into the living spaces for hours. This thermal flywheel effect evened out the extremes between day and night, creating a stable and comfortable environment. The system was perfectly balanced for all seasons. In the summer, when the sun rode high in the sky, wide-eaved porticos and colonnades cast deep, cooling shadows over the same south-facing windows, blocking the intense heat. A perfect example survives in the Roman baths in the city of Bath, England. The complex is meticulously aligned, with the main bathing chambers positioned to receive maximum solar warmth, while the surrounding walkways provided shade for visitors during warmer months. The entire design was a dialogue with the sun's path, a year-round partnership with a celestial furnace. This mastery of capturing daytime heat makes you wonder, how could this solar energy be trapped and held even more effectively, not just for a few hours but through the entire cold night? The next leap was to create a thermal battery, not from a wall but from the earth itself. Beneath the open sky, entire homes were built not to rise above the landscape but to merge with it. Across the vast territories of North America, indigenous communities perfected a form of architecture that used the earth itself as a thermal battery, the pit house. These were not mere holes in the ground, but sophisticated dwellings engineered for year-round comfort. A circular pit, sometimes several feet deep, was excavated, creating a sunken living space. This pit was then framed with a sturdy wooden structure, often made from logs and poles, which was finally covered over with layers of bark, brush, and a thick cap of earth. The genius of this design lay in its profound simplicity. The surrounding soil, with its immense thermal mass, acted as a natural insulator, In the winter, the Earth's own residual warmth, stored from the summer sun, would slowly radiate into the living space, protecting the inhabitants from the bitter cold outside. Conversely, during the hot summer months, the same earthen walls absorbed excess heat from the interior, keeping the pit house remarkably cool and shaded. A central fire pit provided direct heat and a place for cooking, with a smoke hole in the roof allowing ventilation. This created a stable, self-regulating microclimate that required almost no active energy input to maintain. Anthropological studies of tribes like the Navajo, the Plateau tribes, and others show how the design was meticulously adapted to local conditions, with variations in depth, orientation, and entryway design to best suit the specific climate. At heritage sites like the Sun Watch Indian Village in Ohio, reconstructed pit houses offer a tangible sense of this ancient comfort, their interiors feeling silent, secure, and naturally temperate. This was a partnership with the planet, a way of living that understood how to draw energy directly from the ground beneath our feet. It makes you wonder, if the very soil could be harnessed for climate control, what other everyday biological processes did our ancestors learn to tap into? Their next great discovery involved capturing the invisible power of decay itself. The quiet decomposition of organic waste was once a carefully managed source of power. In ancient Chinese villages, sealed pits in the ground transformed everyday refuse into a clean burning flame. These were the earliest biogas digesters, systems that captured the invisible power of fermentation. A typical digester was a simple, airtight pit, often lined with clay to make it watertight. Families would regularly feed it with a mixture of animal manure, human waste, and leftover plant matter, then add water to create a slurry. Inside this oxygen-free environment, colonies of anaerobic bacteria went to work, slowly breaking down the complex organic materials. The key byproduct of this microbial feast was methane gas, which would rise and accumulate in the upper chamber of the sealed pit. A simple pipe, often made from bamboo, would then channel this gas directly to a nearby kitchen, where it could be lit to fuel a stove for cooking or provide light after dark. This was not a haphazard process, but a refined technology. Historical texts from the Han Dynasty, over 2,000 years ago, describe the careful management required to keep the system productive. The feedstock mixture had to be balanced, and the temperature of the pit monitored as the bacteria worked best within a certain range. If conditions were not right, gas production would falter. This ancient innovation provided a remarkable closed-loop system. It turned waste into a valuable energy resource while simultaneously producing a rich, nutrient-dense slurry that could be removed and used as a powerful fertilizer for crops. It reduced the need to constantly gather firewood, preserving local forests and easing the daily labor of rural life. Today, this very same principle is being revived in modern biogas plants across the developing world, proving the timelessness of capturing energy from natural cycles. If ancient farmers could light their homes with gas from a sealed pit, what immense power could be drawn from the daily rhythm of the world's oceans? This question leads us to one of the most predictable forces on the planet, the ceaseless pulse of the tides. The relentless ocean tide did more than just push against the shore. It drove the millstones that fed entire coastal villages. While windmills spun in the breeze and water wheels turned in rivers, a different kind of engine waited patiently for the sea itself to fill its reservoir. These were the tide mills of medieval Europe, masterpieces of patience that turned the moon's gravitational pull into a source of daily bread. The principle was one of brilliant timing. At high tide, a community would open a sluice gate, allowing seawater to rush into a large, purpose-built mill pond. Then, as the tide began to recede, they would close the gate, trapping a huge volume of water inside the pond. now held at a level far higher than the sea outside. With the pond full and the ocean retreating, they had created a temporary waterfall. Only then would they open a channel to let the captured seawater flow back out, channeling it through a water wheel that powered the grinding stones inside the mill. This entire cycle was a slow, powerful pulse, perfectly synchronized with the celestial clock of the tides. It required a deep, localized knowledge of the tidal patterns and a high degree of community coordination to manage the gates and operate the mill at just the right moments. Historical records from the coast of Brittany in France and the estuaries of southern England describe how these mills became the economic heart of their settlements, providing a reliable, predictable power source completely independent of rain or wind. The Elling Tide Mill in Southampton, England, stands as a living monument to this technology. Having ground flour for over 900 years, its machinery still turns today, powered by the same ancient rhythm of the sea. It represents a profound understanding of natural cycles, a willingness to work within the schedule of the planet itself. From the Roman aqueduct to the Chinese Kang, from the Norse horse mill to the Afghan windmill, these 20 lost energy systems reveal a common thread. Our ancestors were not primitive in their power sources. They were profoundly sophisticated in their partnership with nature. They did not seek to overwhelm the world with force, but to harmonize with its existing rhythms. So why were these brilliant systems largely abandoned? The answer lies in the rise of concentrated portable power. The Industrial Revolution offered coal and later oil, fuels that could be burned anywhere at any time, freeing humanity from the constraints of place and season. This was a seductive kind of freedom, but one that came with a hidden cost, disconnecting us from the very systems that sustain us. The lesson for our future is not to literally rebuild Roman aqueducts, but to rediscover that foundational principle of working with the world, not against it. With our modern materials, advanced physics, and global knowledge, we have the capacity to create a new generation of energy systems that are even more elegant, efficient, and integrated than those of the past. The real power was never lost. It is all around us in the flow of water, the push of wind, and the warmth of the sun, waiting for us to listen once more. Coal and oil offered a seductive promise, power on demand. A single lump of coal contained more concentrated energy than a man could exert in a day of hard labor, and it could be burned anywhere at any hour, regardless of the weather or the season. This was the fundamental shift that pushed so many brilliant systems into obscurity. The rise of the steam engine untethered industry from the geography of rivers and windy hills, allowing factories to cluster in cities where labor was cheap and transportation was easy. Why wait for the tide to turn to grind your flour when a steam-powered mill could run ceaselessly, day and night? This new model of centralized power generation was overwhelmingly efficient in economic terms, but it came with a hidden cost, a quiet disconnection from the local environment. As people moved from farms to factories, the intimate knowledge of how to build a windcatcher or manage a tide mill began to fade, becoming the specialized lore of historians rather than the common knowledge of communities. Wars and rapid industrialization further accelerated this loss, as traditional crafts were supplanted by mass production and the urgent need for standardized weapons and supplies. Yet the legacy of these systems was never truly erased. It lives on in the principles they embody. The Roman aqueduct teaches us about gravity-fed efficiency, a concept directly applied in modern hydroelectric dams. The Chinese Kang is a masterclass in thermal mass and waste heat recovery, principles now used in passive solar homes and high-efficiency stoves. Today's push toward decentralized renewable energy, with rooftop solar panels and small-scale wind turbines, is a powerful echo of those ancient, localized solutions. It is a return to the idea of drawing power from your immediate surroundings. So the greatest lesson is not about rebuilding ancient machines with our modern tools, but about rediscovering a mindset. It is a mindset that sees a river not just as water, but as a source of mechanical force, that sees the wind not just as weather, but as a natural engine for cooling and work. This ancient wisdom challenges our modern obsession with overwhelming force and constant consumption, offering instead a model of resilience built on harmony. The real innovation lies in blending this timeless intelligence with the incredible capabilities of the 21st century, creating a future where our power systems work with the planet, not against it. These 20 lost energy systems form a powerful testament to human ingenuity. From the gravity-fed aqueducts of Rome to the methane-capturing digesters of ancient China, each invention reveals a profound truth. Our ancestors were not primitive in their power sources. They were masters of working in harmony with the world around them. They saw a flowing river and understood its potential to turn a millstone. They felt a steady wind and knew it could cool a home or saw a log. They recognized that sustainability was not a modern buzzword, but a practical necessity for survival, a way to balance human ambition with the planet's natural limits. This ancient wisdom is precisely what we need to rediscover today. By studying these elegant systems, we can find powerful inspiration for modern solutions. The principles of passive solar design, waste heat recovery, and decentralized power generation are more relevant than ever in our quest to reduce carbon emissions and build self-sufficient communities. The past offers us a blueprint not for copying old machines, but for adopting a smarter, more resilient mindset. I would love to hear which of these ancient innovations surprised you the most. Share your thoughts in the comments below, and if you enjoyed this journey, subscribe for more explorations into the world's greatest historical mysteries. Together, let's carry the wisdom of the past forward to build a brighter and more sustainable future for everyone.